Okay, so in this screencast, we're going to go ahead and bring it all together. We're going to look at energy conservation in systems that have both conservative and non-conservative forces acting on them. And this is really more like the real world. The good news is it's really not that hard. It's just a little bit of a twist on what we've already done. Not that big of a change. Okay, so let's start off with what we've been looking at before, a closed system. If a system is closed, that means there's no external work being done by outside forces, no external forces adding to or taking energy out of our system. So therefore, the mechanical energy of the system is going to be conserved. That means that the mechanical energy I have initially is going to equal the mechanical energy I have finally at the end. All right. So you can think of it this way: the sum of the kinetic plus gravitational potential plus spring potential energies that I start with initially is going to equal the sum of those same things afterwards. The kinetic plus the UG plus the US afterwards. These two summations have to equal the same thing because these forces are conservative. They store up energy and then release them as kinetic, and so we're not gonna lose any of the energy that we start with. But what if that's not the case? What if there are also external forces that are non-conservative forces acting on the system? In that case, our system is an open system, and that means the mechanical energy is no longer going to be conserved. I'm going to start with one amount of mechanical energy and end with a different amount. In this case, the mechanical energy I start with plus the work I do is going to equal the mechanical energy I end with. Now, listen, let's just make our lives a little bit easier. Instead of using these I's and the F's and all that, we can just be real about this. Look, on this side of the equation, the left side of the equation, that's before, and the right side of the equation, that's after. Okay, and we know that. Okay, so let's just dispense with the I's and the F's and just go on and be lazy. Okay, I like to be lazy. So here you go. So what that tells me is that the kinetic energy plus the gravitational potential energy plus the spring potential energy I start with, plus the work that's done by external forces. And now keep in mind, we say plus work, but that could be positive or negative work, right? I could be adding energy to the system, in which case this mechanical energy is going to be bigger on the side, or I could be taking away. So the mechanical energy I start with here, what I end up with over here is going to be less. Okay, so we're just say plus work with the understanding that work could be positive, it could be negative. Okay, so it's the same thing. We're just throwing work in here. We're saying, okay, we're conserving energy, except we're not because we're adding or taking energy away, right? But other than that, it's the exact same equation. So let's just look at an example, analyze it, and decide whether we should use the conservation of mechanical energy or we add work into it. So what I have here, I say the surfaces of the spring block Earth system shown here are frictionless. Okay, there's your hint. They're frictionless. There's no other force acting on it other than gravity and spring. This is going to be a closed system. So that means that I can just say the mechanical energy I start with is going to equal the mechanical energy I end with because there's no opportunity for energy to be added or taken from the system. So I'm told the spring constant is 2,000 newtons per meter, and I want to know how far this 2 kilogram mass is going to compress the spring before it comes to a stop. Very typical kind of AP question. Okay, so I'm going to say, all right, look, ME I start with is equal to ME I end with. I'm conserving mechanical energy. So I'm going to take the kinetic energy plus the gravitational plus the spring, and I'm going to get the same things afterwards, but they're going to be redistributed. So I'm just going to go ahead and say, all right, I've got 1/2 mv squared for this is going to be 1/2 of 2 times 5 squared. Plus, I have 2 kilograms times g, which is 10, and I'm 4 meters up. So that gives me this here. So I'm going to add these up because I don't have any spring potential on this side. And on this side here, I'm not going to have any kinetic and I'm not going to have any gravitational when it gets down here because I'm going to define this to be zero gravitational potential energy. And so therefore, all my mechanical energy is going to end up as spring potential energy. And so I'm just going to put 1/2 k delta x squared, solve for delta x. I get 32 centimeters or 0.32 meters. All I did is I said I took the sum of the kinetic and potential energies I started with, and I made it equal to the sum of the kinetic and potential energies I ended with. It's a closed system. But let's try change something now. Okay, so now what we have is now the system we had before has friction acting just on this section here. We have an 8-meter section where the kinetic coefficient of friction is 0.25. And the angle here is 30 degrees to horizontal. So this angle here is 30 degrees. Uh, and I want to know how far is the spring going to get compressed now? What we should realize right away, you should be able to say it's going to be compressed less. And the reason it's going to be compressed less is because friction is going to do negative work on this. Energy is going to be taken out of the system by friction and dissipated as heat. Because when this thing slides down here, remember, friction is acting against its motion. And when you have force acting against the direction of motion, it does negative work. So friction will do negative work as it slides down here. So when it gets to here, it's going to have less kinetic energy than it had before. All of this kinetic and potential energy here is not going to be converted entirely into kinetic here and then into spring potential here, because I'm going to extract some energy through friction. So I'm going to now write it this way. I'm going to say, look, the mechanical energy plus work equals the mechanical energy I end with. So the kinetic energy I have plus the gravitational potential energy I have, plus I don't have any spring potential energy on this side, plus the work I'm doing. In this case, I'm doing negative work. So I'm adding negative work is going to equal K, which is going to be 0, plus UG, which is going to be 0, because I'm going to define the bottom of this as being 0 potential energy, is going to give me US. And the spring potential energy, as I said, should be less than what it was before. Before we compressed this spring 0.32 meters, it should be less than that because we've lost some energy to friction. Let's see what happens here. Okay, so let's just try this here. So my initial Ki plus my initial Mg, plus I don't have any spring potential energy, but I have work, and it's going to be negative work because friction is acting in the negative direction. So the amount of frictional force times this distance is the amount of work friction is going to do. And then down here, I'm back to frictionless. So here, I don't have any kinetic energy. I don't have any gravitational potential. I'll just have spring potential energy. All right. So let's just go ahead and substitute in here. I've got 1/2 of 2 times 5 squared. Right. So that's basically 25 joules. Uh, and I have 2 times 10 times 4. So that's another 80 joules I have there. But now I'm going to subtract some energy. So how much energy am I going to subtract? Well, it's going to be the force of friction, which we've already studied in our previous unit. So if you recall, friction is equal to mu times, in the kinetic friction at least, is equal to mu times the normal force. The normal force on an incline is mg cosine theta. So I'm going to say minus, because it's doing negative work, the coefficient of friction is 0.25 times mg cosine 30 times the distance it travels, 8. And that's how much energy I'm going to lose through friction. And that, once again, like I did before, is going to equal 1/2 2000 delta x squared. And when I solve this, I get 0.265 meters of compression, whereas before I got 0.32. I end up with less spring potential energy because I lost energy to friction. All right, let's try another one. This one's even trickier, okay? So I have a person who's holding the 2-object Earth system here at rest. And then the person pushes up on it on the 2-kilogram mass with 16 newtons of force. There is friction in the pulley, and it's going to cause the pulley here is going to gain 3 joules of thermal energy. Its atoms are going to be shaken. So friction causes thermal energy to be gained and then dissipated. All right. So I want to know, how fast is the 3-kilogram mass moving after the person has finished pushing this one 0.5 meters upwards? You might be going, what the heck? It's really not that hard. Let's just try this here. Okay, ready? All right. Now, all right, the first thing we had to ask ourselves is the person's hand doing positive or negative work? Well, this system, if you will, wants to move this way. If the person didn't push on it, this would go down and this would go up. And since the person is pushing the object in the side of the system in the way it wants to move, the person is doing positive work. And how much positive work does the person do? Well, they apply 16 newtons across the distance of half a meter. They're going to do 8 joules they're going to add 8 joules to the system, okay? But now friction is going to do negative work, right? So friction is fighting the way this is spinning and is taking energy out of the system and converting it to thermal energy or heat. So, and I was told that was 3 joules. So I added 8 joules. I did 8 joules of work, positive work. But the friction did 3 joules of negative work. So the net work done is 5 joules. Overall, between me pushing it up and the friction in the pulley, the system gained 5 joules from what it would have otherwise had. All right. So now let's just see what I've got here. All right, so we're moving half a meter, right? So that means that the 3 kilogram mass starts off having 3 times 10 times 0.5. That's 15 joules of gravitational potential energy. The 2 kilogram mass doesn't have any, but over time is, as it moves, is going to gain 10 because it's going to end up with mgh. So 2 times 10 times zero point 0.5, it's going to gain 10 joules of potential energy, while this one is going to lose uh, uh, 15 joules of potential energy. So a better way to think of it is this one starts off with 15 joules and ends with 0. This one starts with 0 and ends with 10. Because you really want to think about beginning and ending. That's the best way to approach this. Okay, let's just put things into our equations and see what we go. All right, the kinetic energy was 0 to start with. The system was at rest. I was holding it. Okay. What was the UG? Well, the UG of this was 15 joules, but the UG of this, I'm defining this to be 0. So it had 0 joules of gravitational potential energy. Now, how much work was done? My hand is going to do 8 joules of positive work, but the friction here is going to dissipate 3 joules as heat energy, so it's taking 3 joules out of the system. That's going to equal the kinetic energy of the system afterwards. Now, this object here, the 3 kilogram one, is going to have 0 joules of potential energy, but this one here is moving up, so it's going to gain 10 joules of potential energy. Okay, so we're just keeping track of who's got how much energy before and after. That's all we're doing. It's just summations. So let's just sum this up here. So 15 plus 5, I have 20 joules here. That's going to equal the kinetic energy plus the 10 joules of gravitational potential energy this one gains. So I'm going to take this 10 away. That leaves me with 10 joules equals 1 half mv squared. But now I got to be careful because this is even though I asked what the velocity of this is, the whole system is moving, right? So I don't just use the mass this, I have to use the entire mass. The whole system has kinetic energy. So I had to say it's equal to 1 half of 3 plus 2. That's an easy place to go wrong, right? We tend to focus on this, but really it's the whole system. V squared, that means, let's see, so I'm going to multiply by 2. That's 20 divided by 5. That's 4. Take the square root, 2 meters per second. All right. I think that's it. Okay. So we just need to practice this, people. You'll see that it seems a little bit daunting right now, but once you start doing it, it's really not that bad. So thanks for watching.